If you've spent any time in computer vision lately, you know the current orthodoxy. When data is scarce, you pretrain with a masked autoencoder and a vision transformer. It's powerful, it's scalable, and it's everywhere. But what if I told you that for a massive class of visual problems, those heavy architectures are actually overkill? Today, we're diving into a paper that challenges that assumption head-on. The authors propose a self-supervised learning framework for texture recognition that ditches the attention mechanisms, skips the ViT, and instead leans on a streamlined convolutional autoencoder paired with Fisher Vector encoding. And surprisingly, it outperforms many state-of-the-art methods while being significantly more computationally efficient. Let's start with why texture recognition is such a unique challenge. Unlike object recognition, where you're looking for distinct shapes and semantics, textures are defined by repetitive local patterns. You get high interclass similarity, where different materials can look almost identical, and high intraclass dissimilarity, where the same texture varies wildly due to lighting, scale, or pose. Standard off-the-shelf CNNs, even when fine-tuned, struggle to capture these subtle statistical differences. And in real-world applications, labeled data is often scarce. That's exactly where self-supervised pretraining shines. But here's the catch. Most modern self-supervised methods rely on vision transformers to model long-range dependencies across the entire image. For textures, that's often unnecessary. The relevant information is highly localized. You don't need global attention to understand the weave of fabric or the grain of wood. You need efficient, local feature extraction. So the authors replace the ViT backbone with a convolutional autoencoder for the pretraining stage. The architecture is straightforward but effective. The encoder applies a series of 3x3 convolutions, followed by 2x2 max pooling, progressively downsampling the spatial dimensions. The bottleneck layer compresses this into a latent representation. The decoder then upsamples the features and uses skip connections to concatenate encoder outputs with the upsampled decoder features at corresponding levels. This preserves high-frequency spatial details that would otherwise be lost during pooling. The model is trained self-supervised by reconstructing the original image using mean-squared error. In some configurations, they even use a denoising variant, where the input is a corrupted version of the image. The key takeaway is that this forces the network to learn the underlying generative structure of the texture, without the computational overhead of self-attention. Once the autoencoder is pre-trained, the pipeline splits. The decoder is discarded, and the bottleneck output serves as a self-supervised feature representation. But the real mechanism kicks in when they combine this with traditional CNN feature extraction. They use an EfficientNet-B5 backbone, pre-trained on ImageNet, and extract local features from multiple convolutional layers. Specifically, they pull from the final layers of Block 5 and Block 6. Since deeper layers have higher channel dimensions, they apply PCA for dimensionality reduction to keep the feature set manageable. Now here's where the technical depth really matters. They don't just average pool these features. They encode them using Fisher vectors. If you're familiar with the bag-of-words model, you know it throws away spatial and distributional information. Fisher vectors fix that by modeling the entire set of local features as a sample from a probability distribution. They assume the features are generated by a Gaussian mixture model. Each Gaussian component represents a visual word in a learned dictionary. The Fisher vector itself is essentially the gradient of the log likelihood of this GMM with respect to its parameters, the means, covariances, and mixture weights. To make this computationally tractable, they assume diagonal covariance matrices. This is a standard approximation that drastically reduces memory and computation, while still capturing the essential variance in the feature space. They compute the normalized gradient components for the means and variances, which results in a high-dimensional vector that encodes how each local feature deviates from the learned GMM. Then they apply Cholesky decomposition to the Fisher information matrix. This transforms the kernel into a simple dot product, meaning you can classify the Fisher vector using a linear model instead of a computationally expensive kernel machine. Before feeding these vectors into the classifier, they apply L2 and power normalization, which is standard practice for Fisher vectors to stabilize the distribution and improve SVM performance. They then concatenate the self-supervised autoencoder features with the normalized Fisher vector features. This hybrid representation captures both the compressed latent structure from pretraining and the rich statistical distribution of the CNN activations. For classification, they use a 1v-rest linear SVM. Interestingly, they leverage a Bhattacharya kernel, which they transform into a linear form using a sine and square root mapping. This allows them to maintain the discriminative power of a nonlinear kernel while keeping the optimization fast and stable. So does this actually work? The results are compelling. Across standard benchmarks like KTH-TIPS-2B, the Flickr material database, and the describable textures dataset, the proposed method consistently beats classical approaches and competes with recent state-of-the-art models. More importantly, adding the autoencoder features to the Fisher vector pipeline boosts average accuracy by over 5% compared to the baseline EfficientNet. Why? Because the autoencoder learns task-specific, low-dimensional representations that complement the CNN features, and the Fisher vector encoding captures the subtle distributional shifts that simple pooling misses. The paper also tests this on a practical application, identifying Brazilian plant species from leaf surface textures. The model substantially outperforms previous literature, proving its real-world utility. The broader takeaway here is about architectural matching. Vision transformers and masked autoencoders are incredible when you need to model long-range, global context. But for domains like texture analysis, material science, or fine-grained classification, the signal is inherently local. By pairing a lightweight convolutional autoencoder with robust statistical pooling like Fisher vectors, you get a framework that is both highly accurate and computationally efficient. It's a reminder that in self-supervised learning, the pretraining objective and the backbone architecture should be dictated by the data's intrinsic structure, not just by what's trending. The code is publicly available, and I highly recommend diving into the full paper if you're working on texture recognition, material classification, or just want to see how efficient self-supervised pipelines can be designed. If you found this breakdown useful, check out the link in the description for the paper and code, and let me know in the comments how you're approaching self-supervised pretraining for your specific domain. Thanks for watching.